7.5 Electron affinity. Electron affinity is the energy change accompanying the addition of an electron to a gaseous atom. In general, electron affinity becomes more exothermic as you go from left to right across a row. This picture shows the electron affinities for the S and P block elements of the first 5 periods. Notice that the trends are not as evident as they are for ionization energy. The halogens, which are 1 electron shy of a filled p subshell, have the most negative electron affinities. By gaining an electron, a halogen forms a stable anion that has a noble gas configuration. The addition of an electron to a noble gas, however, requires that the electron reside in a higher energy subshell that is empty in the atom. Because occupying a higher energy subshell is energetically unfavorable, the electron affinity is highly positive. The electron affinities of beryllium and magnesium are positive for the same reason. The added electron would reside in a previously empty p subshell that is higher in energy. The electron affinities of the group 5a elements are also interesting. Because these elements have half-filled p subshells, the added electron must be put in an orbital that is already occupied, resulting in larger electron-electron repulsions. Consequently, these elements have electron affinities that are neither positive or less negative than the electron affinities of their neighbors to the left. Electron affinities do not change greatly as we move down a group. Fluorine, for instance, the added electron goes into a 2p orbital. For chlorine, a 3p orbital. For bromine, a 4p orbital, and so forth. As we proceed from fluorine to iodine, therefore, the average distance between the added electron and the nucleus steadily increases, causing the electron-nucleus attraction to decrease. However, the orbital that holds the outermost electron is increasingly spread out, so that as we proceed down the group from fluorine to iodine, the electron-electron repulsions are also reduced. As a result, the reduction in the electron-nucleus attraction is counterbalanced by the reduction in electron-electron repulsion. There are, again, however, 2 discontinuities in the trend. The first occurs between groups 1a and 2a. The added electron must go into a p orbital, not an s orbital. The electron is farther from the nucleus and feels repulsion from the s electrons. The second occurs between groups 4a and 5a. Group 5a has no empty orbitals. The extra electron must go into an already occupied orbital, which will create repulsion.
Electron affinity is the energy change that occurs when an electron is added to a gaseous atom or ion. For example, when an electron is added to a neutral gaseous chlorine atom, 349 kilojoules per mole is released. In the case of chlorine and the other halogen elements, addition of an electron to the neutral atom is an exothermic process. Addition of an electron to the neutral oxygen atom is also an exothermic process. However, addition of a second electron to form the oxide ion is an endothermic process. This means that work must be done to force an electron onto the singly charged ion to form the oxide ion, O2-.
The electron affinity is the energy change that occurs when an electron is added to a gaseous atom or ion. For most neutral atoms, energy is released when an electron is added. Because energy is lost from the system in such a process, the electron affinity is a negative number. The electron affinity declines slightly as we move from hydrogen to rubidium in group 1 of the table. The electron added to the neutral atom in each case is paired with the 1 valence shell electron already present. A similar trend of slightly decreasing values of electron affinity with increasing atomic number is also observed among the halogens. However, the values of electron affinity are much larger than for the alkali metals. The values of electron affinity vary irregularly as we proceed from left to right in a given row of the table. These apparently erratic variations can be accounted for in terms of the electron configurations of the atoms. For example, when an electron is added to chlorine, it occupies a vacancy in a valence shell orbital and thus experiences a significant effective nuclear charge. The process is thus exothermic. When an electron is added to an argon atom, which already has a filled valence shell, it experiences mainly electron-electron repulsion and is effectively shielded from the nucleus. Addition of an electron in this case is an endothermic process.